This is an example to show you again how to use Faraday. Here we have a coil with 310 in loops. Every loop is circle like so with radius r 8 centimeters. We have 300 of them. The total resistance is 6 ohms in the 300 loops, and we have a magnetic field turned on at t equals 0 within this coil. This field changes at a constant rate from 20 to 80 in 20 milliseconds. What is the magnitude and direction of the induced current? So the direction is whether it's clockwise or counterclockwise. So now, what we know is Faraday's law: whenever the flux change, there will be an EMF, voltage. And so if you know the voltage and R, then you can figure out the current induced in the circuit. So here is Faraday. It's telling you the voltage, because the change in the flux is minus N d phi dt. This equation is true if we have a function of a, b, or the angle. And so if we are working in a laboratory and doing measurements, then the law is just the EMF is N, of course the minus sign, and then delta phi delta t, finite quantities. Now we explain in the lecture several times that this negative sign is actually Lenz's law. We have a way how to figure out the direction of the current. So let's take care of the magnitude. In this equation, so the EMF, yes, so just N, so this means it's the negative sign. So the flux is AB, the flux phi is A, the area, times B, times cosine theta. Now if we differentiate, so whether A changing, B, or the angle. In our case, it is B that is changing. The area vector A is out by convention, normal to the surface, and B is out is given. And so, also notice here, this field change, clearly going from 20 to 80, the B increase. So the B increase, that means the flux will increase. It's very important to recognize this. The flux in the circuit will increase, going from 20 to 80 millitesla. So now, let's change again. So now this is N delta phi. So this is A, then delta B over delta T. Now what is cosine theta? Well, it's 0, because B and A are parallel. By convention, A is normal to the surface, is B, we are told it is normal to the surface and it is out. So they are parallel, and cosine 0 is 1. So this quantity is 1. So we are left with A and B. We push A outside because it's constant. It is B that's changing. So now this is just N, and the area of loop. Now the change in B in magnitude is final minus initial, that is 80 minus 80, yeah, 80 minus 20, final minus initial. Of course, milli means minus 3. the delta t is 20 milliseconds. Okay, so we get it this. So we can get this number here. Alright, so now we have calculated here what is n times a. N is 300, the area is pi r squared. So it is, then times n is this number. You are welcome to check. Now I am ready to find what is the EMF. The EMF, so it is NA, which is 603, times the change of B, which is 60. So we have dismissed the -3, so 60 over 20. So now what is this? I find 18. So let's do it again. 60 times 6.03 equals divided by 20. Yes, 18.1, so 18 volt. So this is the induced EMF. What about the current? Well, the current I induced is just the EMF over the resistance in the circuit. So that is 18. What's the resistance? It is 6. So over 6, and that is 3 ohms. Alright, so if you know the voltage, you have access to the induced current. The next question, what is the direction? So we have answered this question here, the magnitude. We remember we dismissed the negative sign. What about the direction? Now let me remind you of the steps, how to evaluate direction. You have to remember these steps because I'm not going to give you these steps in the exam. So what is the first step is to identify BO. What is BO? Well, BO is out. How do I know? It is given in the problem, out. Number 2, what is the nature of the change in the flux? Very important. It's not the flux, it is the change of the flux. We agreed B is increasing from 80 at constant rate from 80 to from 20 to 80. So clearly it is increasing. In that case, the relationship between BO and BI induced is like so. They have to be against each other. Why? Because according to Lenz, the circuit will always create conditions that oppose the nature of the change. So in this case, the flux is increasing here, so the circuit will create conditions so that would keep the flux low. And the way to do it is to create a vector B that is against BO. This is BO, by the way. That means in. So here is, we have the situation now, a loop, and we have B in, cross like this. So now number 3, once you find the direction of BO, use the right hand rule. Right hand rule. The rule, there are a few. This is the one situation we have two direction. The B, this is the B induced. Remember, this is B induced. Now the question we have to ask is, what kind of induced current here in the circuit? So that B induced is in. All right. So here, this is the case when you have two directions. So the current, we put the fingers around the current and the thumb will be B. So if you curl your fingers around the loop, the thumb will be in, and that is B. So that means the current is this. Alright, so the current is doing this. if you rotate, so this is the current, which is clockwise. And that's it. So now we have the whole story of this induced current, and these are the steps we have to remember. All right.